So it's not the kind of thing that you just kind of, it's not, the first time you pick up a new tool, you don't kind of reach for Snakemake. It's kind of something that's more like production ready. Like if you, have lots and lots of genomes to process, or if you are going to get, 5 or 6 batches of data, and you want to do the same thing every time, that's when you kind of reach for Snakemake, rather than just like one-off batch scripts or something. So it's kind of a little bit more investment to get it set up, but then when you're going to be using that script repeatedly, its features kind of really bring a lot of benefits. Okay, so yeah, that's basically why I'm going to talk to you about workflow managers. So lots of bioinformatics involves taking some, some funny people on Twitter say bioinformatics is just advanced file format conversion, right? Because you take some fast queues and you turn them into a SAM file, and you turn the SAM file into a BAM file into a VCF, or you turn the fast queues into an assembly, and then you do a blast, and it's kind of all the same data goes all the way through, but it's slightly different file formats. And so this is kind of lends itself very nicely to this workflow computing paradigm, of which Snakemake is one example. Okay, so make this what are some of the advantages of Snakemake or workflow managers generally? So firstly, each job or task. So you can think of a bioinformatics pipeline as having multiple stages. You might do a QC, you might do a re-trimming, and then you might do a de novo assembly, right? And each of those can be thought of as a separate task, and one goes into the other. So in a workflow manager, each job or task can be run within its own environment or container. So that means that you've been learning the last couple of days about environments and containers, and so we can use, especially with Snakemake, we use Conda. We can use Conda environments to make sure that we always have the dependencies that we need to run any particular process. And so that's really built into Snakemake, and it's very convenient. So failures are handled elegantly. So if you've written like a bash script or a Python script to do something like this, if you don't configure it properly, then if one stage doesn't work, sometimes it tries to carry on, right, with the rest of it, and it kind of freaks out, and it's like, produces lots of horrible error messages, or it could even have like fairly nasty consequences for your data. Whereas a workflow manager handles those failures elegantly. It stops if it can't continue. It stops kind of neatly. So that's one thing. But the real gem is that you can restart from like a failed attempt. So say we go back to that example of a genome assembly, and we're doing QC, we're doing some fast QC, then we're doing re-trimming, and then we're doing de novo assembly. Then if it fails at the re-trimming stage, we misspecified the command line or something like that, then when we restart, it will see that the QC was done. It will see the QC, it was completed and finished, and it won't repeat that. It will come onto the stage when it failed. And so not only that, but if it manages to process half the data of the re-trimming stage, it will see, okay, I've done half the data, all I need to do is the ones that were not done. So that's really nice, and it's actually really hard. Well, it's a lot of effort to like code that up manually, if you were doing like a Python or Bash script. So they're portable, and this kind of varies a little bit. In terms of like exactly how portable they are, but because you specify a Conda environment or a Docker container for each process, as long as those are kind of publicly available Conda environments, then in theory you can just send your pipeline to someone else, and when they run it, it just pulls in the Conda containers from that public repository, and it makes it kind of more portable. rather than, if you just install everything on your local machine, then if you send it to a collaborator, they have to install everything on their local machine as well, and they have to have all of those skills to do that. So it makes things a bit more portable. So they're also highly scalable. So the same code can run on your laptop or on an HPC with only minor configuration changes. And actually, not only can just the same code run, but has anyone worked on an HPC? So on an HPC, you have to use what's called a job script. And you write a bash script basically that is going to run the job, and it has some specific things about the resources you're requesting, and it's a real pain basically to write job scripts. So you have a script, you have to have a script that writes all these job scripts, and then if they're dependent on each other, then you have to code that in. So okay, you need to look for this process ID, blah blah blah. It's a real headache, and it takes a long time. But with a workflow manager, it's just all baked in, and they have most of them are compatible with the common HPC job schedulers, so called, and it means that you can kind of go from working on your laptop, and you can use that HPC much more efficiently and with much lower, less of a learning curve. And yeah, it's efficient. If jobs are parallelizable, if they don't depend on each other, then the workflow manager will run them in parallel. Okay, any questions so far? Okay, so there's lots of different workflow managers. So the first, there's lots of different workflow managers. The two you've maybe heard of, or the three you've maybe heard of, are probably Snakemake, Nextflow, and Galaxy, or those are the most common there. The others are slightly less popular. And so the two that we teach on this course are Snakemake and Nextflow. And so Snakemake has a little bit of an easier learning curve. So that's why we start with that one. But it's slightly less powerful and than Nextflow. So, but Snakemake is really, it's kind of, I used it definitely as my full-time thing for 3 or 4 years, and it can do most of the things that you want to do. One thing it can't do so well, or it doesn't handle as well as Nextflow, is the Docker containers. So Snakemake goes really nicely with Conda. So that's kind of what we're going to focus on. Okay, so Snakemake is a little bit different from a normal script, a normal bash script or a normal Python script. Normal Python script, you kind of start, at the top of the file, and that's the first thing that happens, and then the second that you have the second thing that happens, below that, and the third thing that happens below that. So that's the normal thing, right? You start at the top and you work your way down, and you read through, and you do step 1, step 2, step 3. So Snakemake scripts are a little bit different, and they rely. They rely on a slightly different way of thinking about it. So basically, the way to think about it is, what's the final thing that I want out of this pipeline? What's the objective of this pipeline? So in our example earlier, it might be a genome assembly. So I want a genome assembly in a faster format. So that's the final thing that I want out of the pipeline. Okay, so then what's the process that's going to give me that thing? So what's the process that's going to give me a genome assembly? Yeah, de novo assembler. So, so you get a genome assembly out of a genome assembler, right? So that's the process that's going to give you that thing. Then what are the inputs for that process? So it's like you start with the last thing that you want, the genome assembly. Then you say, okay, how do I get that genome assembly? Well, I get it with a genome assembler. Okay, so what are the inputs for that process? Okay, so the inputs for that process are, maybe trimmed reads, nice reads with all the errors kind of taken out. Okay, so trimmed reads are the inputs for that process. Okay, where do those inputs come from? Right, where do the inputs for the trimmed read process come from? Yeah, they're the raw reads, right? So then, what's the process that gives you that input, and so on. So it's kind of this, okay, what's the final? You start with what's the final thing that I want, and then you say, what's the process that gives me that? What are the inputs for that process? And then, okay, then you kind of start again. Okay, well, what are the inputs for that process? What are the processes that give me that? And then you go round and round until you have completed the whole thing. And you go kind of round and round this loop. Until you kind of make it up to whatever your input file is. So yeah, we don't, in the examples we're going to be doing today, we don't go around this too many times, because we don't want to give too much of a complicated workflow. But this is the kind of outline of how to think about it. Basically, the fundamental thing is that you have to think about what's the last thing I want, and then work your way backwards. So this is just kind of laying this out again, because this is really the tricky thing about Snakemake. So what's the last thing we want? We want a de novo assembly. What's the input for that de novo assembly? It's trimmed reads. What's the input for that? It's raw reads. So now if we start making it a little bit more like Snakemake-y. Okay, so the process here is read trimming. The input is going to be raw reads, and the output is going to be trimmed reads. So this is so when you're giving something in as files, that's a kind of little bit of a special case. And that's the fundamental input of what you're giving in, from outside of the Snakemake process. And then so these come in as files, and then they come onto the second process of where the process is assembly, the input is trimmed reads, which you'll note is the output of this one, and the output there is the assembly, which is the final thing that we want. So this is one of the kind of funny things is that you need a rule in Snakemake that it doesn't really do anything. It doesn't have a process. It doesn't have a process in a normal way that you would think of as a bioinformatics process. Its function is to kind of pull the data through the pipeline. It's not a processing stage that really gives you something different out. It's you can just think of it as a rule that pulls the data through the pipeline. And this is the final thing. It's stop when you've got this. But this whole thing is right, I'm going to pull the data through the pipeline. That's how to think about Snakemake. And so this rule, is the kind of pulling rule that you put. at the end of your pipeline, but usually at the beginning of your script. Okay, so just a little bit more information about the kind of mechanics of Snakemake. So it's based on Python. So within a Snakemake file, you can usually just use Python anywhere in that file, and it's based on Make. So some of you, if you've installed some tools from scratch, you might have used a Make file on Linux. So it's kind of Make has this similar philosophy of like pulling things through. So that's hence the name, Snake for Python, Make for Make. So it splits your workflow into separate rules, one rule per process normally. And then the rules have a rule name, they have input files and output files usually, and a command that actually does the job that you want to do, that specifies exactly the job you want to do. So this is an example, just of one rule. So we have the keyword rule, then the rule name that we've decided, it's BWA map. We're going to do some mapping of reads to a reference genome with BWA. Colon, indent, because we're kind of in Python world, so this is like the Python syntax. And then we specify the input. So the input is just a pair of strings in this case, one specifying a reference genome and the other specifying a FASTQ. Then we're telling it our output is going to be a BAM file. So again, just a string but points to a file. And then the shell, this is how we specify the actual process that we're going to be doing. So this is just kind of equivalent, more or less, of what you would type on the command line, with a few kind of formatting differences. So on the command line, you would just type BWA mem, and then you would give your reference genome and your FASTQ in that order, and you would pipe it, which is why it's okay to do it as long as it's in this order. So input, this is a Snakemake keyword. That comes, it knows that you mean this, basically. That's what's been entered at the input stage. And then pipe, like Unix pipe, to SAMTools view, input file, and then this flag is telling it that the input file is a SAM and the output file is a BAM. And then this says to stream to standard out, I think. And then we pipe to output. And then output is again this Snakemake like special formatting, and it just knows that we mean this string. So this is just gonna map these reads to this reference. It's gonna pipe them to SAMTools, which is gonna convert that SAM that's output by BWMM into a BAM, which is gonna be saved to this file. So that's like one rule. Is that kind of, anyone have any questions? What questions do you have about that? Yeah. Sorry.
For the map and that's the rate story.
I think you probably have to create it prior, yeah. But I'm not 100% sure.
Sure.
Yeah.
The file memory, do you have to have quality description or maintain the same file memory?
Yeah, we'll come to that, yeah.
So that's the one I want.
Yeah, I think it has to be specified in this order, input, output. Yeah, input, output, shell. Okay, so if the contents of that rule that we just looked at, that we just went through, was saved as this file, mymappingpipeline.smk, so Snakemake. So to run it, we would just say, as long as we'd installed Snakemake, we would say snakemake -s mymappingpipeline.smk, and then that would run that script. So that's the main way that I personally invoke kind of Snakemake commands. So the other way you can do it, which I don't really like very much, but they describe it as the best practice, is you save the contents. So rather than saying mymappingpipeline.snakemake, you just save it in a file called snakefile, and then all you do is run snakemake with no arguments in that directory, and it will see, okay, there's a snake file in here, I'll pull that, I'll run that one. So I don't really like that because it's not very explicit. It kind of relies on that file being the only Snakemake file in that directory. That's just not really how I work very often, but just so you're aware that this way can also work fine. Okay, so kind of Alan's point, was a good one. That script wasn't really very useful, right? It's just like one input file. There's not really any advantage. We're not taking advantage of many of the workflow manager features by just doing that. So now we're going to start to make things a little bit more interesting and a little bit more scalable by using kind of more wildcards. So these are wildcards. So again, we just have these two input files. It's the same, rules doing the same thing. Input data is the reference genome. But now here we have in curly braces sample. So this is also like a little bit tricky to get your head around sometimes. But sample is basically, when this runs, Snakemake is going to look in data samples, and it's going to look for everything that matches this kind of pattern. So everything that has a some kind of string followed by .fastq. And it's going to look in there using like a regular expression, if anyone knows what that means. But basically it's just going to look in here, and it's going to look for everything that ends fastq, and it's going to add that. It's going to add that to its to-do list, and it's going to process all of the fastqs that it can see. It's going to take all those fastqs as a list, basically, and it's going to run this process for each one that it finds. So the kind of clever thing is that when it finds a file that ends, for example, let's say we have two files like sample1.fastq and sample2.fastq. So when it sees those two files, it makes that sample1 and sample2. It kind of says, okay, that's now my sample name. It kind of does this like clever thing where it's like, okay, this is how you're specifying that you want to find the files. So we're going to take this as kind of the thing that you're interested in. This is like something unique about that sample that we're going to use to like name things further down the pipeline. So now the output, when the input is sample1, the output is going to come and follow and be sample1.bam. And then that is fed forward into this. So the output, this output is then going to be sample1, and then on the shell command, we've specified the input and then the output as well. So that will be sample1 and sample1. Sample1 here and sample1 there, and then when it's time for sample2, it will kind of flow through and match both. Okay. So that's kind of one of the other little tricky things to wrap your head around in Snakemake as well. So we call these named wildcards. So in this case, we're calling it sample, but we could call it anything that we wanted, pretty much. As I just said, it finds all the files matching the pattern, directory data, within that directory samples, anything that matches this pattern, and runs that rule on them. And yeah, that sample wildcard propagates all the way through the rule. Okay, so that's kind of useful, but again, that's not often how I work personally. Because maybe you don't want to run the workflow on every single fast queue in that directory, right? Maybe you only want to run it on some. So you could also just specify the names, these kind of names of the samples that you want to run. So here we have just a Python list, because remember that Snakemake is just kind of Python with a few added extra bits, quite a lot of added extra bits, but we just specify a list in the same way as we would in Python. So we say samples equal sample 1 and sample 2, and now we have a very similar rule, BWA map again. Now we're like just being a bit more explicit, and we're saying that for the input, what we're going to give this a name now. We're going to be more explicit and say it's the reference genome equals this path to the reference genome again. And now we're going to use another little thing that Snakemake has added to Python called the expand function. So this is really, really common. This is kind of in almost every Snakemake script that I write. And now we're kind of our named parts of the input are going to be the reference genome and something we're calling fast queues. So fast queues equals an expand of this string with this list. So what this does is it says, okay, give me this string with every element of samples in place of sample. So all that's going to do is produce 2 strings, because we only have 2 elements in our samples, and it's going to 2 strings, one data samples sample1.fastq, the other one data samples sample2.fastq. So yeah, this is like a common way that I kind of actually use Snakemake in reality, and then the same thing, it propagates through sample wildcard, named wildcard propagates through the script into the output and the shell commands. Okay, so that's like a one-step thing, but again, that's not really super useful. So how do we do a kind of more realistic 2-step Snakemake workflow? So again, going back to our first example of read trimming and de novo assembly. So BBD UK is a read trimming software of the BB map package. So the overall outline is this rule is going to trim our reads and produce kind of quality reads that don't have any low quality bases in. And this rule is shovel, Torsten Siemens kind of spades assembler modification, which just does a de novo assembly. So this one does the read trimming, this one does the de novo assembly. So going back to our example before, this returns back to the first example we spoke about. Okay, so this is just at the moment about how these two link in, and then on the next slide we'll talk about how to get data into this. But this is just about okay, sorry, I forgot to mention. Did I forget to mention? No. Okay, so we learned on the last slide about how input, you can have reference genome and fast queues, and you can name these things whatever you want. Here we're doing a similar thing, but we're saying, okay, it's a bit more realistic now. Usually we get paired reads as part of Illumina, right? So we have a read 1 and a read 2. And then we're going to have outputs that are also read 1 and read 2, but trimmed. Yeah, that's what happens when you do a read trimmer, right? You run a read trimmer, takes in a pair of fast cues, it gives you back out a pair of fast cues, and you just kind of want to extend the name of the fast cue to have the tool that you ran on it, so you know where that fast cue came from. And then in the shell file, we specify. Okay, so now we're saying rather than just like input as we were doing previously, we're specifying using the dot syntax which part of the input we want. So when we use this named wildcard, input.r1, it knows that we're referring to input r1. It's that we're referring to this one. And then in2 is input.r2. So it knows that we're input here is like a kind of keyword for this one. And it knows that we want that one then. And then similar with the output, output.r1 and output.r2. Okay, so that's just a slight extension of what we have learned previously. And then the next, how do we combine this data with another rule? And this is where that kind of, okay, what's the process that I want to do? What's the input for that process? Right, so the process we want to do now is shovel, so de novo assembly. What's the input for that process? It's trimmed reads, right? So trimmed reads are made by our BBDUK rule. So this just slightly extends the syntax with the dot. So another keyword, rules, are just all the names of the rules that you have in your file, so that you're telling it which rule you want to get the output from. So we start off with rules, and then BBDUK, because that's the name of the rule that we want to take the output from. We want the output from it, so we can also use the input from it as well if we have, if we want to do it that way. But the more natural way to think about it is I take the output from one rule as the input for the next one. So output.r1. So it knows that rules.bbduk.output.r1. That's this guy. It's just a string, but it's a string that points to a file. And same with R2, it just comes directly from the output. So this is really advantageous because now if we decide, oh, I'm going to switch, I want to change this, how we're calling this, and I want to say like, I don't know, clean reads or something, then we just say clean reads, and then we don't have to change this input specification. It just takes it, it just knows you want the output from this rule. So that's really nice. And then, and then now the final thing, the shell, and now we just have to specify that it's, now we want the, we have to use the wildcard stuff. So when we want to use the sample wildcard in the shell, we just have to specify wildcards here. So that's a little gotcha that will trip up many people, including myself, quite frequently. So you just have to specify in the shell command that you have to, when you want to use the sample wildcard, you have to say wildcard.sample. And then just the same thing. So input here just refers to this input. Because there's no kind of, we're not specifying the rule. Okay, so I think we're getting towards the end. I can sense that you're all eager to get to grips with Snakemake for yourselves. So how do we like finish this off? So we need the pull bit, right? We need to like pull the data through. So this is how we do it, and the norm is that you have this rule at the top of your file, and that you call it all. So these are like, I think they're just norms. I don't think they're strictly specified. Maybe that it has to be at the top, but I think all is just that it's a norm. But I highly recommend you stick to that. And so this rule is a bit different from the others. It only has an input. It doesn't have output and a process. So this is like the pulling bit. It doesn't do anything other than just like pull your data through the Snakemake workflow. So the funny bit here is that this is where you specify your to-do list. So you specify your to-do list and you use your expand statement in the last bit of the workflow that uses those file names. So that's like another little tricky thing. So you use this expand statement in the last bit, which in this case is just the kind of final rule that's pulling everything through. And then we're expanding. So root_dir is a parameter set here. And then sample is going to come from this to-do list. So we've specified a to-do list somewhere above. Then for every sample in the to-do list, it's going to say, before I can finish, I need files to exist that match every file that matches, I need files for everything that matches this kind of regular expression where sample is every sample in the to-do list. And so it said, okay, I need something for all of those. Okay, how do I make that? Oh, sorry, what's the output that gives me that that input? Okay, so it finds this rule and it says, okay, what I need is this. I need this file as my input for this rule. What's the process that gives me that as an output? Okay, the process that gives me that, this is what the program does. The process that gives me that as an output is this shovel rule. Okay, because this is the same as this. Okay, so it says, okay, for this rule to pass, to be satisfied, I need to run this rule. Okay, what's the input for that process, for that rule? Okay, the input for that rule is the BBDUK output. Okay, what rule do I need for that? To run for that, I need to run this one. So it knows that this is the first one that has to run, this is the second one, and this is the last one that's going to be satisfied, that's going to pass, because this is the last, this is the guy at the end that's pulling everything through. Okay, so don't worry if you're feeling a bit zonked. This is definitely not a way that we normally think about doing stuff in programming. It's definitely a different paradigm, but it's really powerful. And I'm sure that by the end of the day, we've got all day to work on this. By the end of the day, it will click. Okay, so just very briefly, so what Snakemake does when it actually runs is it converts the file into what's called a directed acyclic graph, or a DAG. And so this is kind of a slightly more complex DAG. We don't need to go through this, but if you like DAGs, then you can look at that in more detail. We can talk about that. Okay, so now we're going to do the practical exercise. Practical exercise 1, which is based on the Snakemake documentation. So I think you should have access to these. Ooh, maybe not actually. Yeah.
You can also post the link, just slip straight into Slack. Is anybody not able to access our Slack? What's this?